Hello everyone, welcome to this chromatography webinar. It's the masterclass number 5, Flash and Prep HPLC applications. My name is Birke Götz and I'm Global Product Manager for Preparative Chromatography at BUCHI Labortechnik Flawil in Switzerland. Now, I think it's already 1.5 years ago when we started with these master classes, and so far what we did, we focused on the theory of Flash and Prep HPLC. So we talked about detection options, about sample loading, sample injection, about how to improve resolution, and also about consumables. And what we will do today is we will actually now discuss what this means for different types of compounds. So let's get started. First of all, if you have any questions, so please use this question panel in the bottom right hand corner, and then either at the end of this session or per mail we will answer your question. This is the agenda for today's webinar. So first of all, we will have a very general look into application development. And afterwards, we will go a little bit deeper into different compounds. So proteins, we will cover vitamins, natural products, lipids, carbohydrates, small molecule drugs, and at the end, I will just give a very short summary. So, application development. The number of applications in Flash and Prep HPLC is constantly increasing. And with this also the variety of the compounds. So the differences in these compounds is so huge that it's actually not possible to have or to define a universal approach to purify these compounds. And since every sample is unique, and with this also the method for the purification. And there are actually several questions which you have to ask yourself during method development, and for no compounds it will be the same answers. So for example, you have to ask yourself, in which solvent is my sample soluble? Or which stationary phase retains my target compound not too strong and not too weak? Does the method allow to inject my sample as a liquid? Or is my compound chromophoric or not? And what we will do in the following is we will go through the different types of compounds which I mentioned before, and I will give you some tips and some infos on what you should keep in mind regarding these 4 topics: the mobile phase, the stationary phase, the sample loading, as well as the detection. And we will now start with the peptides and the proteins. So proteins consist of amino acids. There are in total 20 different amino acids. And in solutions, these proteins form these highly organized 3-dimensional structures, which are then closely related to their biological function. And for example, the proteins can give the shape to cells, or they can respond to signals transmitted from the environment. So they actually play a very important role in nearly all fundamental processes in living cells. And they are frequently studied for their potential as therapeutic drugs. And peptides are just a smaller version of proteins. So they contain a smaller number of amino acids, which is around between 2 to 50 amino acids. Everything that's bigger or more than 50 amino acids is then a protein. So, mobile phases. You're using reversed phase to purify peptides or proteins. This means you are working with a water mixture with a less polar solvent, for example, acetonitrile, isopropanol, or ethanol. But acetonitrile is actually the most popular one because it's volatile. It can be easily removed from your fraction after the collection by evaporation. It has a low viscosity and it has little UV absorption. And what you also do typically you add TFA to your mobile phase for pH control and also to enhance the retention. Now, since this reverse phase chromatography uses polar organic solvent as a mobile phase, the method can actually only be used for compounds which can handle these harsh conditions. So this type of chromatography actually only works well for peptides, or small peptides and small and more stable proteins, which can then, after the purification, spontaneously reform. If this is not the case, then you have to choose a different chromatography method. This can be child filtration or size exclusion chromatography or ion chromatography. Now the stationary phases. Peptides, for peptides and proteins, you're using alkyl bonded phases with different pore sizes, and which one you select actually depends on the molecular weight and also on the polarity of the compound. Let's start with the molecular weight. Very small peptides and proteins you can purify with standard C18 pore sizes between 60 and 100 angstrom, which you see here on the picture. Now, as soon as your compound is getting bigger than 5 kilodalton, you have to go for bigger pore sizes, because only then it's possible that the compound enters into the pores and uses the surface, because you need, as higher the surface of your particle size, the better it is for your resolution, for the purity. So if you have a bigger one, then you need to switch to pore sizes between 200 and 300. Standard pore size is 60 to 100 angstrom. Another thing is that it has been shown that for bigger compounds, C4 and C8, so smaller alkyl chains, they give you better selectivity, so a better purification. So that was the size. Now, if we have a look to the polarity of the compound, then it's C18 is the most unpolar phase. So as soon as you have something which is a little bit more polar, it might happen that you don't get any retention on the C18. So then you would try the C8 or the C4 because it's less unpolar, and then it's very likely that you can get your mixture separated. Then there's another point. You have to decide which particle size you want to use. Is it prep HPLC or is it flash? So in prep HPLC, you're working with very small particle sizes. You get a higher resolution. In flash, it's the opposite. You have the bigger particles, and you have you can load much more than in prep HPLC, but you get a lower. You're somehow limited in resolution. Now, since these peptides proteins after synthesis, it's the fact that the impurities, they might be very similar to the target compound. So it could be that it's very hard to, or not easy to separate them by a flash, and you really need small particle sizes. So that's why prep HPLC is typically the preferred method to purify peptides and proteins. So we come to the sample loading. Well, if you're working with prep HPLC, so the only choice you have is liquid loading. That's it, that's given. If you, we come to flash, we come later, but let's stay with the liquid injection. If you have very hydrophobic mixtures, then it's recommended to work with lower polar solvents, for example, acetonitrile. If you have something very hydrophilic, you would go for ethanol, isopropanol. These are the typical solvents used. If you have something which is very, very high hydrophilic, then you need to add some DMS or DMF as an injection solvent, because then you can keep the sample volume as minimal as possible. And that's actually important because if you have very large volume of your sample, let's say its sample volume is the same as your column volume, then it can happen that you get band proteining, and this is not what you want because this has a bad influence then on your resolution. So we typically say a maximum 10% of the column volume should be the volume of the sample. And then, yeah, we come to flash chromatography. I mean, still there are some people who uses flash chromatography. It works for their sample. Then it's perfect because Flash chromatography, the cartridges are much less expensive than prep HPLC columns. So if you can go to flash chromatography, then you can either inject via liquid or via a solid sample. Now for detection is actually super easy because peptide proteins, they absorb UV. Typical wavelength length is 280. This actually only works if you have amino acids like tryptophan or tyrosine. If you don't have, then just go for 205 nanometer, and then it's also possible for you to detect the peptides or the proteins. Now we come to some application examples. So for all the compounds which we will go through, I will show you some application examples from our lab. Here we have an example which shows the effect of the polarity of the phase. We worked here, or let's say my colleague in the lab, he worked with a mixture of lysozyme and BSA. He used prep HPLC columns, and what you see on top, this is a column, a C18 white pore column, and on the bottom it's a C4 white pore column. So the only difference here is really the polarity of the phase. Otherwise everything was the same. What we see is on top, we don't get these two peptides, proteins, separated, but on the bottom you get a nice separation. So in this case, on the top, somehow these two compounds interacted the same way with the phase, and on the bottom with the C4, they interacted in a different way, and this is how you could get it separated. Then we come to another example. This is the effect of the pore size of the phase. At the top, we have for both a white X mixture, and on the top, my colleague worked with a C18 column, and on the bottom it was a C18 white pore. So it was 200 to 300 angstrom pore size versus the typical 60 to 100 angstrom for the C18. What you see is that when you go for the bigger pores, the peaks get better separated. They are sharper. Just have a look at the first peaks. So these peaks are sharper, and you really get a nice baseline separation of the first two peaks. So a nice effect of the pore size to the separation of the peptides and proteins. Okay, and now we already come to the next topics. These are the vitamins. Vitamins are essential nutrients which are needed for the proper function of an organism metabolism. So, for example, they help to heal wounds, or they boost our immune system and more. And humans can actually absorb the vitamins either from the food and environmental sources, or they can take it in synthesized form as tablets. And these vitamins, they can be classified as either water soluble or fat soluble. And the solubility of a vitamin then determines how the vitamin acts in your body. You see here on in the table below, you see the different vitamins with their different functions, and you see the solubility. So we have most of the vitamins are actually water soluble, as you can see, and just 4 are fat soluble, and that then determines the function of the vitamin. I've also shown here 2 famous vitamins, the water soluble vitamin C. I think that's something everybody knows, and we also have here the fat soluble vitamin A, for example, with these long alkyl chains. Okay, and now we have a look, what do we need to know regarding mobile and stationary phases? So vitamins, first of all, they can be purified under normal phase as well as reverse phase conditions. If you have something which is water soluble, I think it's clear you would first of all try reverse phase. So what you have a water mixture with some low concentration of an organic solvent, acetonitrile or methanol. You use some buffers for pH control, for example. And then there's one thing, if your sample is highly, or your compound is highly polar, then it might be that you need to work with very high water concentrations, more than 95%. And in this case, what you have to do, you cannot work with a standard C18. You would need to work with a water-stable C18. Those are available on the markets, no problem. And what you can do there, you can work with, for example, 98% water at the beginning of your run. I will show you an example later on, but just that you know, if it's very, very polar, there are some phases available which don't collapse. I mean, the C18 typically, if it's not AQ stable, the C18 change, they would collapse if you come with 98% water. Okay, so reversed phase. Then we have the fat-soluble vitamins. They can be actually purified via reversed and normal phase. So in reverse phase, you just use less polar solvents, such as DCM, acetonitrile, methanol, but no water. Yeah, I think that's clear. If it's really highly unpolar, you would go for the normal phase and you use highly unpolar organic solvents such as hexane or ethyl acetate. Now, in vitamins, we have the situation that some of these compounds are very highly polar. In this case, you have a third option, and that is HELIC. And HELIC stands for hydrophilic interaction chromatography. And we will have a closer look to this. What is this? So if you have a highly polar vitamin and you go for normal phase, what can happen is that your compound is very sticky at your face, because the normal phase, the stationary phase is highly polar. So it sticks, and you would actually need a lot of solvent to get it eluded, or maybe it's sticky at all at the face. In reverse phase, what can happen is that since the stationary phase is super unpolar, that there's really no interaction of your compound with the phase, and then you don't get any separation. The vitamins just run through the cartridge. So, and in this case, what you can do, if both modes don't work, you go for HELIC. And HELIC is something in between normal phase and reverse phase, because what you do, you work with a polar stationary phase. That can be silica, amino, diol. And but you are using reverse phase solvent conditions, using water. And you see this here on the right side. So the mobile phase forms actually a water-rich layer on the surface. And then you have on the top, you have the organic mobile phase. That's the orange one. And what you do actually during the elution, you increase the water content. And then you can elute the vitamins from your from the stationary phase. So it's the opposite in reverse phase. You just use the solvents like reverse phase, but you do a different gradient, because in reverse phase what you would do is you would start with very high water content and reduce this water content, and here you increase the water content. Acetonitrile, that's the typical solvent used for HELIC. That's because it's very good miscible with water. It has a good HELIC retention. It has low viscosity. But okay, there are also other options in case the acetonitrile doesn't work. And for the phase, you just take any polar stationary phase, silica, aminodiol, or whatever. Sample loading. Well, if you work with prep HPLC, you go for liquid loading. If you go for flash chromatography, then you would have in principle two options, solid loading and liquid loading. But solid loading is a bit the problem, since you are applying heat to get rid of the solvent. This can be destructive for some vitamins. So in this case, you would go for liquid loading, and here it's easy. You just, I mean, the vitamins just need to be soluble in the starting condition, and then you just inject it. So it's actually, yeah, anyway, liquid loading is the most easiest way to inject something, or to inject the sample. Detection, the vitamins can be detected via UV absorption, but the UV spectra of the water and the fat-soluble vitamins, they actually significantly vary because they have different structures. And so our recommendation is actually then to use a DAD, a diode area detector, because then this records really the full UV spectrum. And the nice thing is with the DAD, it also confirms you the purity and also the compound identity, because every compound has a typical UV absorption spectra, and with the DED you can actually see this. So it also eliminates the need for any TLC of your fractions if you have a DED. Now we will have a look to some application examples from our lab. The first one is we are comparing here a C18 and C18AQ, which I just mentioned before, prep HPLC column. So my colleague had here a mixture of 7 different compounds, amino acids, including aminobenzoic acid and caffeine. And in the first run, he used a C18. And in the second run, which you see, he used a C18 AQ. And what he did in the first run, he actually used a water concentration. He started at 95% because it was 5% of methanol. And for the C18AQ, it was possible for him to start with a higher water content. He started at 97% water, because you see here where the red arrow is, it's at 3 minutes. He went from 3 to 7% methanol. So, and because he could start with higher water concentration, he could go with a more flat gradient in the second run. And if you look at the first peaks, you see on the top 2 peaks, and on the bottom you see 3 peaks. So you have a better separation working with C18AQ, because you can go with a more flat gradient and you can start with higher water concentration. We have another example. Here what we did, we compared reversed phase and helic with 3 different compounds. In the first run, this is a C18 flash cartridge. And in the second run, it's a diol cartridge. So, and in the first run, this was just a normal reversed phase. We started with very high water concentration and increased the methanol over time. And there was no separation, as you can see here. And in the diol, what we did, we actually started with very high acetonitrile concentration and then increased the water concentration. And then you see the 3 compounds get nicely separated by the helic. So actually very, very simple. Okay, now we come to the next topic, and these are natural products or extracts. A natural compound that is defined as a chemical substance that's produced by a living organism. And generally, a natural product is produced by primary or by secondary metabolism pathway. And as you can see here on the picture is that the primary metabolites, which can be carbohydrates, lipids, proteins, nucleic acids, they are involved directly in the growth of the organism. And the secondary metabolites, that can be alkaloids, phenolics, sterols, and so on, they are produced for defense purposes. So this is the difference between the natural products. And let's have a look what we need to know regarding mobile and stationary phases. The choice of the solvent is actually made on the choice of the extraction solvent. I think that's clear. So if you have an extract that's more done in hexane, DCM, methyl acetate, so more unpolar and non-water miscible, then you go for normal phase. As soon as you're working with alcohol or water for the extraction, you choose reversed phase. And for the stationary phase, I mean, yeah, it can be any. It can be normal phase like silica diol amino. It can be reverse phase like C18, C8, C4, everything possible. Another decision you have to make is then on the silica particle size. If you go for flash, in flash you have the option typically between 15 to 50 micrometer particle size. In prep HPLC, it's between 5 and 50. I mean, all of these techniques, they have their pros and cons. If you work with big particle sizes, it's much cheaper. You have a low back pressure. You can work with high flow rates. You can work with high sample amounts typically for flash chromatography. The limitations is just the resolution and the low loading capacity. The pros for the pros and cons for the small particle sizes, I mean, yeah, benefits is you have a bigger surface, you get a better resolution. Limitation is I mean, the smaller particle sizes are higher in costs, and you get a higher back pressure. That somehow limits you in the flexibility of the flow rate. But what's typically done in any way for natural products, since the extracts, they are super complex, you combine flash and prep HPLC. So you start with big particle sizes, you do it like a pre-purification step, and then you collect the fractions where you think or where you know your target compound is in there, but not at very high purity. You collect this and you re-inject this on a prep HPLC column to get then there the high resolutions. Okay, sample loading. Yeah, I mean extracts. Normally natural extracts, mixtures, they are high in volume. If you inject this as a liquid, then you can either do this manually, or when you really have large sample amounts, you would go for an injection pump. If you have very large volumes, which you want to load at once, then there is the recommendation to go for solid loading, because as I mentioned before, I think it was for peptides, if your sample volume reaches a volume which is more than 10% of your column volume, then you might get band protoning, and then you're losing the resolution. So then you would go for solid loading. You just absorb your sample on the support material, typically silica. You evaporate your solvent and you place the sample in front of your flash cartridge. Yeah. So, and then afterwards, you would go after flash, you would go for prep HPLC, and prep HPLC anyway, it's only possible to do liquid loading. Detection, yeah, I mean, we just saw nature products that can be lipids, that can be proteins, that can be carbohydrates, that can be anything. So, and all of these different compounds, they have different different structures. Some absorb UV, some don't absorb UV. Some absorb it maybe differently. So here is really the recommendation to combine UV and DLSD. And again, DAD is actually here the choice, because you don't know, maybe you don't know how your, oh no, sorry, the DAD, I mean, if you know your absorption spectra of your target compound, then it's for you, it's very easy to see if this is really your product or not, because you have the full absorption spectrum. So combination of UV and LSD. We have a look to some application examples. Here is the combination of flash and prep HPLC. My colleague here worked with a red chili extract, and he wanted to isolate capsaicin, which you see here on the top, the structure. So he used the flash cartridge first. That was a silica cartridge, and you see many different peaks because, yeah, as I said, this is just coming from an extract and full with different compounds. And in these fractions between 9 and 11, that's at time of 15 minutes, this is the fraction he collected because he saw from the DAD that actually this is the capsaicin. So he collected that and he re-injected that peak into a prep HPLC column, and he actually, you see, he got it very nicely separated just because of the smaller particle sizes. He used 10 micrometer instead of 40 micrometer. He also changed a little bit the mobile phase from water acetonitrile. He used CN-C18, the first one he used silica, DCM acetonitrile combination, but at the end, yeah, he could perfectly purify actually the capsaicin at high purities. Good, we have another example for natural products, and this is now on the higher resolution using smaller particle sizes. My colleague worked with a Boswellia extract. In both cases, the first one he used a 50 micrometer silica particle size, and in the second one a 20 micrometer. And if you just look at the chromatogram, you immediately see more peaks for the second run than for the first run. just if you have a look for the first peak, for example, you see on top, you see one main peak, and on the bottom you have at least 3 peaks, which shows you that, yes, a better separation because of the 20 micrometer, the smaller particle sizes. Okay, good. We have a third application example, combination of using UV and ESD. Here, this is a clove extract. And there are these 2 compounds, eugenol and caryophyllene, number 1 and number 2. And there is super interesting to see because the eugenols, you can only detect via UV because it's a flavor, so it's volatile and it gets evaporated in ESD. So it's not possible to detect it via ESD. And the second one, caryophyllene, is non-chromophoric, so you can only detect via ESD. So a very nice example here for nitrogen extracts combining UV and ESD, which makes it possible for you to really detect everything which is in your sample mixture. Good. We come to the next compound family. These are the lipids. Lipids, these are a diverse group of molecules and that are important, very important because they are involved in intermediary metabolism. They are important for membrane structures, for signaling, and for protection. And they can be categorized into several groups, into fatty acids, into glycerophospholipids, into sphingolipids, sterolipids, prenolipids, and so on. So we have many different ones. And you just see here, some examples of lipids. I think cholesterol, this is something everybody knows, a triglyceride, for example, a phospholipid, a free fatty acid. So very versatile compound family. Let's have a look at the mobile and the stationary phases. So yeah, lipids are soluble only in organic solvents, so no water. But still there are 2 possibilities to purify the lipids, normal phase and reverse phase. Normal phase, what you do, you use hexane, ethyl acetate or DCM. Yeah, that's how it's typically done. And if but you can also go for reversed phase, for example, but then you would go for a non-aqueous condition. So this means you just you use, for example, DCM, acetonitrile mixture or methanol, but no water, and then this actually allows you to separate very lipophilic compounds, which are maybe not possible to separate via normal phase, but you can then switch to reverse phase and just avoid using any water. So 2 possibilities to purify the lipids. The lipids, this is actually a very good example where maybe normal phase, the silica and the standard C18 don't work, because maybe the C18, the lipids are too sticky, and maybe under normal phase conditions, there is no retention at all. And then for this family, these phases which are in between are very interesting. And in between, between silica and C18, and that's amino and diol. You see this here in the graph. If you look, amino and diol, they have a polarity which is just between silica and C18. And the nice thing with amino and diol is you can work under normal phase and reverse phase condition. We come to some examples later on. Sample loading, lipids, they can be injected as a liquid, but only when you use organic solvents. I think that's clear. If you really have a solubility issue, then you could go for a solid loading. That's also an option when you work for flash chromatography. Detection, that's very interesting because lipids, they have only little UV absorbance. Traditionally, what users did was they used a refractive index or low wavelength UV, but there you have several limitations. For example, the poor sensitivity, the gradient incompatibility, or problem with the absorption characteristics of the mobile phase when you work with low wavelengths UV. So the solution is actually either you, after you collected your fractions, you take the fractions and you do TLC to see where is your lipid, or a very nice alternative detection is the ELSD. And here it's no problem to get the lipids detected because it's a completely different detection technique. We have some examples. This is a mixture of glycerate with monostearine, diastearine, and tristearine. And we have on the top a reverse phase condition using C18. And on the bottom, we have a normal phase condition using amino. And what you see on top is that the unpolar solvent has been increased over time, the DCM, the methyl chloride. And for the normal phase, my colleague used the same solvents, but he went for normal phase condition, which means he decreased the unpolar solvent during time. And what you see, I mean, both techniques, both techniques more or less work. You see all the compounds, but you have a different order. I just wanted to show you this in an example with what can be the effect of changing the mode, changing the phase. Good. Now we come to the carbohydrates. A carbohydrate is found in plants, in animals, in microorganisms, and they have numerous roles in living organisms. For example, energy storage. They are components of coenzymes. They are also the backbone of the genetic molecule. They play actually many vital roles in our life. And the carbohydrates is a natural occurring compound, or it's a derivative of such a compound with the general formula with the carbon, the oxygen, and the hydrogen. And depending on their molecular weight, the carbohydrates can be divided into low molecular carbohydrates, such as mono and disaccharides, and more complex ones, which then have high molecular weights and are called the oligo or the polysaccharides, which you can see here on the pictures. Now, if we have a look to typical mobile and stationary phases, carbohydrates are soluble in water and alcohol. They are rather poorly soluble in most organic solvents, so therefore you are working with water mixtures and you combine it with acetonitrile, for example, which then works as the weak solvent. Now carbohydrates, they are highly polar, and if you go for a C18, and C18 is very unpolar, what can happen is that you don't get any retention of your carbohydrate at the stationary phase. So in this case, like for lipids, it's again these phases in between which are very interesting. And this is the amino and the diol. An amino is a typical phase which is used for carbohydrate purification. Because you can work under reverse phase condition, so you use the water, but you take a little bit a less unpolar phase, the amino and the diol. Sample loading, I mean, they are soluble in water. You go for liquid loading and you have them actually always injected as a water mixture. Detection, that's very similar to the lipids because they lack chromophores. And also in the past, refractive index were used, or low wavelength UV, or post-purification via TLC. And here again, the ELSD is the perfect detection technique for carbohydrate. It's actually everywhere used. And I just want to show you some examples. Here the combination of UV and ELSD. We have 3 different carbohydrates. And you see, it's actually, I mean, the glucose, maltose you only see with ELSD. That's the green line. And acarbose, you see a little bit of a UV absorption, but very, very low. So only the ELSD made these mixtures or made carbohydrates visible. And here, by the way, we used an amino cartridge and a water acetonitrile mixture. Okay, and now we come to the last family of molecules we are talking today, and these are the small molecule drugs. So the small molecular drugs, they are pharmaceuticals, and they are defined as organic compounds with a low molecular weight and a very simple structure, and they can be manufactured via synthesis, chemical synthesis. Typically, the masses are between 0.1 and 1 kilodalton. And the main advantage of these molecules is because they are so small, they can pass through cell membranes and they can reach the intracellular targets. And they are very, very stable, and they can be administered orally. And I'm showing here two famous examples. We have on the left side the aspirin, and on the right side we have the diphenhydramine. That's an allergy blocker. Good. And mobile and stationary phases. Yeah, what can happen if you synthesize something? It's the same actually for peptides and for proteins. The impurities can be very similar to your target compound. So what for small molecule drugs, what is often done is the combination of flash and prep. Pre-purification, and then afterwards the high resolution purification. And the small molecular drugs, they can in principle, they can be purified via normal and reverse phase condition. But the point is that for small molecule drugs, it's crucial to be water soluble, because then it's a better absorption in your body. So the general objective is here to use reverse phase under water conditions. But still, if there are some molecules which are really not possible to purify via reverse phase, then you could go for the normal phase as well. I'm just bringing here again these pros and cons of normal phase and reverse phase, which I mentioned already in some of the other chromatography masterclasses. Just want to repeat this, that for normal phase, the big advantage is that the mobile phase can be easily evaporated. And the silica is pretty cheap. The con is definitely that, the organic solvents are more expensive, and environmental concerns is also a big topic for this normal phase solvents. And silica, even though it's very cheap, it can be used only, or it's only suitable to use it for single use. And that's then different in reverse phase. Reverse phases are expensive, but normally you can use it at least 10 times, 20 times. I mean, I even heard of 50 times you can use your C18 cartridge. And in C18, the big advantage is you can work with water mixtures. You don't have any problem with or you have a lower problem with environmental concerns. The mobile phases are cheap. But at the end, it depends on your application. If you don't get it separated to reverse phase, you have to try the normal phase. Okay, sample loading. Yeah, you can load these small molecule drugs, either liquid or solid, for flash, and it just depends on your compound's polarity and on the chosen purification technique, how you load it, but in principle both is possible. Regarding the detection, most of these small molecule drugs are UV absorbing. They have for sure different UV absorption spectra. In some cases, if you go for normal phase, the solvents can interfere with the compounds absorbing at very low UV wavelengths. Then ELSD would be also here for small molecule drugs an option. And again, the best is always to combine ELSD and UV to really make sure that you see everything, and not only see your target compound, but also see your impurities. Okay, so that's it for the detection, and then we just come to some application examples. Here we have the combination of UV and ELSD. This is these are 3 compounds. Let's say from the synthesis, the starting material as the final product, which has been purified here, and you see that the first one of your starting material, you can only see via ELSD and not via UV. If you would have chosen here only UV, you wouldn't have seen this impurity. And it's then a problem if the impurity overlaps somehow with your target compound. In this case, all are perfectly separated. It's not a problem. But as soon as you would get an overlap, it's an issue if you don't see your impurity. Okay, and now we are already at the summary. So as I mentioned at the beginning, there is no universal approach to perform separations of all sample types. The samples or the compounds are so different, so that for each one you really have to decide what mobile phase, what stationary phase, what detection, and how to load the sample. I just gave you some info, some tips today on different compound families. Maybe you remember for peptides and proteins, you need to have a special focus on the stationary phase, polarity and pore size. The vitamins can be purified via very different modes. We learned about normal phase, reverse phase, and helic. Helic is really a great option, not only for vitamins. As soon as you have something which is highly polar, you can try the helic. For natural products, it's crucial that you combine flash and prep HPLC, that you purify your highly complex extract before you go and the rather expensive prep HPLC. By the way, if you combine flash and prep, it also extends the lifetime of your prep HPLC column. Lipids and carbohydrates, yeah, they are not chromophoric. Here you definitely need ELSD to make them visible. And small molecular drugs, they are highly versatile, but normally they can all be easily detected via UV. So that's it regarding this masterclass number 5 on the applications. Please, you can follow us. We have Bart's blog for colorful researchers. Here we are not only talking about purification, we also talk about evaporation, about freeze drying, for example, and spray drying. You can follow us on LinkedIn, on Facebook, and on Instagram. So thank you very much for your attention. And please, if you have any message, any question, leave it here on the chat. You can also send an email to marketing@buchi.com. Thank you very much and bye-bye.